Get started for the last session. So I mentioned before Pedro's talk that he was a scientific organizer and lecturer 4 years ago at TASI 2015. So we're having a TASI 2015 reunion this afternoon. David Simmons Duffin also gave some excellent lectures on CFT and the bootstrap 4 years ago, and he's back to tell us about CFT and Lorentzian signature.
Okay, thanks. It's really a pleasure to be back here. I really enjoyed being at TASI last time, and so I'm sure this time will be just as fun. I turned off the ringer on my phone, so Greg isn't going to interrupt us anymore. These are lectures on Lorentzian CFT. Both Lorentzian and Euclidean conformal field theories appear across theoretical physics. One way in which Lorentzian CFTs appear is as describing quantum critical points. So these are systems with, they're quantum mechanical systems with one time direction and d-1 spatial directions. And in particular, the symmetry group of these systems includes the Lorentz group, SOD-1,1, and that's a subgroup of the larger Lorentzian conformal group, which we'll talk more about later. Meanwhile, Euclidean CFTs, one thing that they do is describe equilibrium statistical systems at criticality. They have d spatial directions, 0 time directions, and their symmetry group includes SOD, the rotation group in d dimensions. We, in principle, don't have to study these subjects separately because Euclidean and Lorentzian CFTs, and more generally quantum field theories, are related to each other by Wick rotation. We'll be more precise about what that means in a moment. It's a way of analytically continuing correlation functions from Euclidean signature to Lorentzian signature and back. And so it means that the data of a Lorentzian CFT is in principle the same as the data of a Euclidean CFT. And so you might ask, why should I bother studying the theory in one setting or another setting? Now, the point is that even though the data of a Lorentzian CFT is the same as the data of a Euclidean CFT, so namely by CFT data I mean operator dimensions and OPE coefficients, these same quantities appear in both contexts. But there are non-trivial observables that are very difficult to formulate in Euclidean signature, and also constraints that come from studying these observables that are deeply hidden in the Euclidean correlators. If you just study Euclidean correlators, it's very difficult to see these constraints and why they need to be there. But if you go to Lorentzian signature, everything suddenly becomes clear. We'll see how far we get in this course. But some examples that we're going to try to talk about are, first of all, unitarity bounds. I like this example because you can study unitarity bounds easily enough in Euclidean signature. And I think Slava did some examples for you in his lectures. Yes?
I did.
You did? Good, excellent. Okay. So you guys have seen unitarity bounds, and I'll show a different derivation of the unitarity bounds in Lorentzian signature that actually has some nicer features than the Euclidean derivation. Another example that we'll try to get to in this course is the average-null energy condition. This is a positivity condition on CFT data that you can't even really formulate in Euclidean signature because it involves an intrinsically Lorentzian operator. And I'll try to explain what the ANIC is, some of its implications, and also hopefully get to a proof of the ANIC. And another property of CFTs that becomes clear in Lorentzian signature but is deeply hidden in Euclidean signature is analyticity in spin. In fact, in Euclidean signature, that sounds like a totally ridiculous notion. And so we'll explain what it is in Lorentzian signature and hopefully derive it. Okay? So that's the plan. Are there any questions? Yes?
Does this Wick rotation only make sense in unitary theory, or can you also extend it to non-unitary theories?
So I'm going to discuss Wick rotation next, and we can see the conditions required for it to make sense. Okay, so that's the thing we're going to start with. We're going to look at Euclidean versus Lorentzian correlators. And these are related by analytic continuation. This analytic continuation, many properties of this relationship between Euclidean and Lorentzian correlators are easy to understand already in quantum mechanics. So we're going to think about, we're going to model a QFT, and I'm not going to use conformal symmetry for a while. We're just going to talk about a general QFT. We're going to model QFT as a quantum system with Hamiltonian H. And the important features of this Hamiltonian are that, first of all, it's bounded from below. So I'll assume that the spectrum of H is non-negative. And furthermore, that there's, for simplicity, I'll assume there's a unique vacuum state. And all other states have positive energy. And the important property for us is that H is unbounded above. So this will generally be true of a quantum mechanical system with an infinite number of degrees of freedom, in particular in a quantum field theory. And we'll see that the fact that H is unbounded from above will force us to think about correlation functions in this theory as living in very specific domains, and will force us to move around singularities in a very particular way. Okay. So let's start in Euclidean signature. So in Euclidean signature, the time evolution operator is e to the minus tau times h. Okay, so tau is some Euclidean time. For the moment, we're going to take tau to be real. Because h is the spectrum of h is positive, if we evolve for a positive amount of Euclidean time, then this operator causes exponential damping in time. And this corresponds to the fact that correlation functions in Euclidean signature decay as you move the points away from each other. So this is the time evolution operator. And we can define Euclidean local operators, Heisenberg picture operators, by conjugating by this time evolution operator. Okay, so I'm going to use the subscript e to indicate that we're in Euclidean time. When tau is equal to 0, there's no distinction between a Euclidean local operator or a Lorentzian local operator, so I'm dropping the subscript in this expression here. So these are Heisenberg picture operators in Euclidean signature. And we can compute correlation functions of these operators. And an example correlation function would be something like a vacuum expectation value, O1 Euclidean of tau 1, On Euclidean of tau n. And plugging in the definition of these operators, let's also use the fact that the vacuum is killed by the Hamiltonian. So that means that we just get O1 of 0, e to the minus tau 1 minus tau 2, h, O2 of 0, dot, dot, dot. And the last term is On of 0 acting on the vacuum. If we like, we can be even more explicit and insert a complete set of energy eigenstates here. And here, And then we get a sum over these psi's, over these energy eigenstates of some transition amplitudes times exponentials of the energy. Okay, so here's our first key observation. The key observation is that only time-ordered correlators make sense in Euclidean signature. Okay, so why is this true? Well, so first of all, let's consider the case where these operators happened to have been time ordered. So we're going to consider the case where tau 1 is bigger than tau 2, and so on up to tau n. The nice thing about the time-ordered configuration is that these Euclidean time evolution operators are well behaved. So we have something like e to the tau 1 minus tau 2 times h. And if the times are in this order, then this factor is positive. And as I said before, this operator leads to exponential damping. And in particular, high energy states are exponentially damped. Okay, so the contribution from the sum over psi 1 gets damped at high energies. And this is crucial for getting the correlation function to converge, to actually make sense. The reason is that these transition amplitudes generically behave like powers of energy. So they behave like e to some power, where here e is the energy of the states involved in the transition amplitude. And as a consequence, if you have exponential suppression in energy, that's easily enough to overwhelm the behavior of these transition amplitudes. And consequently, the correlation function will be finite. And there's an exercise in the notes that I'll post on the wiki where you can verify for yourself how these transition amplitudes behave with energy. So this is good. This operator exponentially damps high energy states. Okay, so that case is very nice. Now you can guess what the problem is if we have something out of time order. Suppose that we tried to consider tau 2 bigger than tau 1.
Why does it grow with energy in scale of 12? Doesn't it decay?
Okay, well, let me write the exercise on the board. So, is there another board here? Oh, there is. Okay, good. All right. Okay, so the exercise is, let's consider a Euclidean two-point function. In a one-dimensional CFT. And this is just fixed by, well, so first of all, we can write this in terms of a sum over states of some transition amplitude between the vacuum and that state squared times e to the minus tau times the energy of the state. Okay, this is just a special case of the formula that I wrote there. On the other hand, we know that this is 1 over tau to the 2 delta, where delta is the dimension of the operator. Okay, that's just fixed by dimensional analysis. And so the exercise is to compute the following density. the density of these transition amplitudes in energy space. And show that this is indeed proportional to a power of energy. Essentially, the reason for this power of energy, and I'll just write the answer, so it's going to be like e to the 2 delta minus 1. The reason for this is because there's a power law singularity. So the fact that Euclidean correlators have power law singularities as local operators become close to each other translates into the statement that these transition amplitudes grow like a power law of the energy. Okay? So this is an exercise.
Question.
Yes?
Is this only true for CFT?
It should be true in any theory whose short distance behavior.
Can you repeat the question?
The question was, is this only true for CFT? And the answer is, it should be true in any theory whose short distance behavior agrees with the CFT, or is sufficiently close to a CFT. So for example, it would be true in an asymptotically free theory. Okay, so that's the exercise. I'm going to cover up the exercise so I can keep writing. So we considered this case, and the point is that this operator exponentially damps high energy states, and that makes the correlator convergent. But if we now consider a case where we put the times in the wrong order, then this operator, this time evolution operator, is wildly unbounded. It leads to exponential enhancement of high energy states. And this exponential enhancement immediately leads to the correlator diverging. So, this is why when people write Euclidean correlation functions, they usually don't bother to say time-ordered Euclidean correlation functions. They just say Euclidean correlation functions. And it's because only time-ordered correlation functions make sense in Euclidean signature.
Another question.
Yes?
Also, you say only time order, so for 2 points is sort of obvious, but for 0 points, if like there are intermediate time intersections that are reversed orders, so there are chances.
Right. So I only talked about this time evolution operator here, but the idea is that there are time evolution operators like this between each pair of local operators. So if any of those is out of order, then you get exponential enhancement in energy of the states that are flowing between those local operators. Okay, so none of the times can be out of order. Okay, so for this reason, when people write Euclidean correlators, they usually don't even bother to say that it's time ordered. The Euclidean correlators are defined to include time ordering, and let me just write what time ordering means. So the correlator without any decoration means a time-ordered correlator, and it's a Euclidean time-ordered correlator. And so this TE means Euclidean time ordering. And what that actually means is that it's a sum of different functions for each ordering of the times. So there's the function that we just studied times a theta function that enforces that the times are in the correct order. And then plus permutations. Okay, so good. So these are the natural observables in Euclidean signature, and these also happen to be the things that are computed by the Euclidean path integral. Okay, so Euclidean path integral naturally gives you a time-ordered correlator. And so this is a nice object in Euclidean signature, and in fact, it's really the only object that you can study. The situation in Lorentzian signature will be very different. Questions? Okay. Good. So now let's talk about analytically continuing to complex times. Now, the theta functions can't be analytically continued in a natural way. So instead, when I say analytically continue a Euclidean correlator, what I really mean is pick an ordering, pick the function associated to that ordering, and analytically continue that. Okay? So we're just going to talk about the function of these times, which is the one we've been studying so far. And we're going to think about analytically continuing it as a function of the taus. Now the claim is that this is a perfectly excellent thing to do. And in fact, f can be continued to a holomorphic function in the region where the real parts of the taus are ordered like this. Okay? So as long as we maintain this ordering of the real parts of taus, we can actually make the taus complex variables, and everything will work fine. Not only will everything work fine, but we actually get a holomorphic function of the taus, in particular a function that doesn't contain any singularities. Okay? So why is this true? So the idea is, let's just write tau I is equal to epsilon I plus I times t sub I, where epsilon I and t sub I are real. Okay, so this is just notation for the real and imaginary parts of tau. And when we plug this in, the time evolution operators, they used to have the form e to the minus difference in Euclidean times times the Hamiltonian. And now we get an additional term like this, e to the minus I times t1 minus t2 times h. But this additional term just inserts a bunch of phases into the correlator. So if we stay in the regime where the epsilons are ordered in this way, then we know that this part of the time evolution operator already gives exponential damping for high energy states. So the sum over states, if we organize it, the sum by energy, is beautifully well behaved. Now if we stick in these phases here, nothing like that changes. The value of the sum is different, but it's still exponentially convergent in energy, and therefore the correlator is perfectly fine. And we could study derivatives of the correlator with respect to any of the times, and we would find that those derivatives all converge as well. So we get a holomorphic function in this region. Any questions? Okay. Good. Okay, so that's the story for Euclidean correlators. If you are sticking to real Euclidean times, then only time-ordered correlators make sense. However, if we fix an ordering, we can then analytically continue the resulting Euclidean correlator to complex Euclidean times, as long as we stay inside this nice region where the time evolution operators give exponential damping of high energy states. Yes?
So this means commutative of Euclidean operators is infinite?
Absolutely, that's right. So that's a good point. So in particular, so the comment was, does this mean that commutators of Euclidean operators are infinite? And the answer is yes. It doesn't make sense to study a commutator of two operators at different Euclidean times. Because if you try to do that, then at least one of the terms in the commutator would contain an exponentially unbounded time evolution operator. There are some exceptions. So for example, a conserved charge is totally fine because the conserved charge at one Euclidean time is related to the conserved charge at another Euclidean time. And you can always move it so that it's at the same Euclidean time as the thing you're taking the commutator with. But yes, for local operators, it doesn't make sense to consider a commutator when they're at different Euclidean times. Okay, now that leads us to Lorentzian signature. Where the situation is very different. Okay, so in particular, we'll be able to study commutators and all sorts of nice stuff like that. So in this case, the time evolution operator is e to the minus I t times h. And the Heisenberg picture operators in Lorentzian signature are just defined by conjugating by this time evolution operator. In particular, this is equal to O Euclidean of tau equals I times t. Now, it's easy to get confused by factors of I and -1 when you're in this business, but you should feel confident that there's a correct answer for all of those factors. And the correct answer is determined by following this recipe that we're following now. So where is the thing that breaks the symmetry between I and -I? It's this. It's the choice that Schrödinger made early in the 20th century to write the Schrödinger equation with I times d by dt instead of -I times d by dt. That choice fixed this to be the Lorentzian time evolution operator, and that in turn fixes this to be the relationship, the correct relationship between Lorentzian and Euclidean time. Okay? So there's only one correct way to Wick rotate, and you get it by writing down this equation. Okay, so these are our Lorentzian operators, and we can go ahead and study a correlation function of them. And the correlation function looks the same as what we had in the Euclidean case, except now, instead of these Euclidean time evolution operators between the local operators, we have Lorentzian time evolution operators. Oops. Minus I t1 minus t2 times h O2 of 0 dot dot dot. Now, unlike in Euclidean signature, there's nothing particularly special about any ordering of the times. Okay, so this time evolution operator is oscillatory whether or not t1 minus t2 is positive or t1 minus t2 is negative, and there's nothing particularly better about one sign of t1 minus t2 or the other. So as a consequence, it makes sense to think about Lorentzian correlators with any ordering of the operators. And as a special case, you could think about a commutator of Lorentzian operators. And that's a perfectly fine thing to do. So there are many more types of observables, and you could ask, well, if there are so many observables in Lorentzian signature, but there's only one kind of observable in Euclidean signature, how are we supposed to go back and forth between them? And that's one dictionary that we're going to work out in a second. But before explaining that, I want to mention an important consequence of the fact that the Lorentzian time evolution operator is oscillatory and not exponentially damping. And the consequence is that the sum over energies, so we could take this expression and insert a complete set of energy eigenstates as we did here, and we would just get e to the I times various things. The sum over energies is the sum over phases, and it's no longer guaranteed to converge. And in fact, the sum over phases in general does not converge to a nice function. So Lorentzian correlators are not actually functions of the times. You need to do something to them to make the sum over high energy states converge before you get a well-defined object. And the thing that you can do is, so the thing that you need to do is smear the correlators against some test function. So the idea is that the high energy states are contributing rapidly oscillating phases, and the way to get the contributions of those phases to converge is to average them out a little bit. And if you integrate against a smooth function, then the more rapidly oscillating the phase is, the smaller the average will be, and therefore you'll turn the sum over energies into a convergent sum. So the technical statement, so first of all, let me define some terminology. So I said that you can consider Lorentzian correlators in any order you want. And if we fix an ordering, then this thing is generally called a Whiteman function. And I'll adopt that terminology from now on. So when I say Whiteman function, I mean a Lorentzian correlator with a fixed ordering of the operators. Okay? I just mean this object. And having defined that terminology, I'm going to now explain why it's bad terminology. The correct statement is that Whiteman functions are not functions. Instead, they're what are called tempered distributions. So let me define what that means. And the fact that Whiteman functions are tempered distributions is a really useful thing to know. Tempered distributions are actually much nicer objects than they might initially seem when I introduce them. And you can do some interesting things with Lorentzian correlators using the fact that they are tempered distributions. And one of them that we'll hopefully see later in this lecture is derive the unitarity bounds in a really beautiful way. Okay, so let me explain what a tempered distribution is. So first of all, a distribution on a space of functions, curly f, is a continuous linear map to the complex numbers. So if we have a distribution T, then it maps this space of functions to the complex numbers. T is linear, and the word continuous means that if we have a convergent sequence of functions, f1, f2, dot, 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 then the sequence of numbers, t of f1, t of f2, dot, 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 is convergent. Now, we usually, as physicists, write formally that this distribution evaluated on a function is the integral of something against the function. So integral dx from minus infinity to infinity, I guess I'm using t as my variable, f of t times capital T of t. But the point of introducing the notion of a distribution is that this capital T of t doesn't actually have to make sense. So there's an example that all of you are very familiar with, which is the Dirac delta function. So we could have T of t is a Dirac delta function of t minus t naught. And this thing is not actually a well-defined function. It doesn't have a value at t equals t naught. Instead, it's really defined by saying what its pairing is with a test function. So the Dirac delta function is defined by the statement that the integral dt of f of t times delta of t minus t naught is f of t naught. This linear map from the space of functions to complex numbers is continuous and linear, and so it satisfies the conditions that we need to have a distribution. Okay? So a distribution is just a generalization of the usual notion of functions. It's something that naturally needs to be paired with a function to get a number. So when we are talking about a space of distributions, we have to say what space of functions they act on. And depending on the types of functions they act on, we get different spaces of distributions. And the space of distributions that's appropriate for Lorentzian correlators, if we ask that question, the answer to the question depends on sort of how bad the oscillatory phases are in Lorentzian correlators. Okay? Depending on what the oscillatory phases are like, we may have to integrate against nicer and nicer test functions to get something finite. So the claim is that the right test function for quantum field theory is the Schwartz space. And Schwartz functions are basically functions that are as nice as you could possibly ask for. So the definition of a Schwartz function is, so I'll call the Schwartz space fancy S. A function is in the Schwartz space if it decays faster than any polynomial at infinity, and furthermore, all its derivatives decay faster than any polynomial at infinity. So a function is in the Schwartz space if these quantities are bounded for all m and n greater than or equal to 0. Okay? So they can't have singularities, because if they had singularities, then the derivatives of those singularities would lead to something unbounded. So they're beautifully smooth and they decay to infinity. And so the claim is that in order to get something sensible out of a Lorentzian correlator, what you need to do is actually integrate it against Schwartz test functions. And from now on, I'll use the term Schwartz function and test function interchangeably. So the claim is that this thing is well defined.
So if the test functions have to be really nice, that means the correlators can be really nasty.
Exactly. The nastier the correlators, the nicer you need the test functions to be. Any questions? Okay, so the central claim is that the correlation functions in a Lorentzian QFT are pretty nasty, but they're nice enough that you can smooth out all the oscillations and get a finite result if you integrate against Schwartz functions, Schwartz test functions. Yes?
So what about the spatial coordinates? In principle, the coordinates are functions of spatial potential with the average or evaluated distribution in a Schwartz function that also depends on that.
Right, that's a great question. So I'm
Can you
just...
repeat the question?
The question was, what about spatial directions? Should we also use Schwartz functions in the spatial directions? And the answer is yes. And later, I'll introduce spatial directions. So for now, I'm just modeling our QFT as a quantum mechanical system with an unbounded Hamiltonian. Later, pretty soon, hopefully, I'll introduce the spatial directions and talk about what the statements are in a d-dimensional quantum field theory. Any other questions? What does tempered mean? Good. So yes. So a tempered. Thank you. So a tempered distribution is a distribution on the Schwartz space. Okay, so it's a fancy way of saying distributions on the Schwartz space. And if you go around saying tempered distribution, then people get, ooh, they get really impressed. They don't know exactly what you're talking about. So I definitely recommend adopting this terminology. Okay. Yeah, good. So this is the definition of a tempered distribution. And so the claim over there that Whiteman functions are tempered distributions is the same as the claim that these quantities are well-defined. Yes?
So well-defined in the sense that if we define some quantity that is not well-behaved, then it gets renormalized? Yeah.
Well-defined in that you get finite numbers, as opposed to trying to evaluate a Dirac delta function at 0. In fact, I should say, not only are they well-defined, but if you have a sequence, a convergent sequence of test functions, then the sequence you get by doing this integral will converge as well. So that's an important part of the definition of a distribution. So not only do you get finite numbers, but the finite numbers behave nicely as you change the test function. Yeah? Is there an order of the integration?
Yeah.
Oh, good. So actually, yes. So that's another component of the statement that Whiteman functions are tempered distributions. The general statement is that actually I don't even have to pick a function that factors into different test functions. I can pick a general function of the times, and the claim is that the integral is convergent for a general function of the times. It doesn't matter what order you did the integrals in. Yes?
So if we smear the correlator by the test function, how should we connect it with the physical meaning, actually? Because we
Great.
artificially introduced the test functions.
Good. So let's see. Let me make some. Well, I'll make some comments about that. So actually, can I wait to answer that question for a little later? Yeah. So you might think that this smearing thing doesn't look like a great idea because we just took our observables and we introduced a dependence on a giant space of test functions, and why on earth would we do that? The answer depends on the physical situation, and I'll make some comments about that later. Other questions?
A Gaussian is a Schwartz function, right?
Absolutely. A Gaussian is...
The Gaussian around HT1.
That's right. Yes. That's right. Gaussians are beautiful Schwartz functions. Okay. Good. So, okay. So why are Lorentzian correlators tempered distributions? I want to give you a quick argument in the case of a one-dimensional theory. I won't prove it in the case of a d-dimensional theory. For that, I'm going to have to quote the Osterwalder-Schrader reconstruction theorem. But I want to do this. I'll give you an argument in one dimension. And in part, this argument will show, I hope it will give a hint of some of the nice properties of these Lorentzian correlators. Okay? So, and also in order to state the argument, we have to finish the dictionary between Euclidean and Lorentzian correlators. So how do we get to these Lorentzian correlators? The idea is, so remember that we had these Euclidean correlators that were holomorphic functions of their arguments in some nice region. So we could study this Euclidean correlation function. And this is holomorphic as long as epsilon 1 is bigger than epsilon 2 down to epsilon n. Now, the way to get a Whiteman function from this thing is to just, so we want to just set all the epsilon i's to 0. So remember that we had this dictionary between, so just from the definition of these Euclidean Heisenberg picture operators and Lorentzian Heisenberg picture operators, we had that a Lorentzian of t was equal to a Euclidean of I times t. And so if we can just set the epsilons to 0, then we'll get a Whiteman function. The problem is that we can't just set the epsilons to 0, because when we do that, we move to the boundary of the region of holomorphicity, and there's no guarantee what we're going to get. So this is the boundary of the region of holomorphicity. And the answer is that when we set the epsilons to 0, we do not get a function. Instead, we get a tempered distribution. And so let me explain how we get a tempered distribution. The statement here is that the boundary value of a holomorphic function with a nice property that I'll mention in a second is a tempered distribution. Yes?
It is a holomorphic function of differences of two adjacent arguments, right? It's not of those.
Well, I can think of it as a holomorphic function of all n arguments, if I like. It happens to be translation invariant. Okay, so so what we're going to do is we're going to think about the boundary value of a holomorphic function in one variable. So we'll just do this as an example. Boundary value of a holomorphic function of one variable. And let's assume that as we approach the boundary of the region of holomorphicity, this function has at most a power law divergence. So I'll assume that as epsilon goes to 0, this holomorphic function is bounded by a power of epsilon times some function of t that grows at most polynomially at large t. Okay. And the claim then is that if we study a of epsilon, which is the integral of this holomorphic function, f of epsilon plus I times t, times the test function f of t, then A of epsilon has a beautifully finite limit as epsilon goes to 0. This is a bit non-trivial because this condition on the holomorphic function allows it to become singular on the boundary. And indeed, we're going to look at examples where the boundary value of the holomorphic function really does have singularities. So it's non-trivial that when we integrate those singularities along the other direction, the one that's not going to 0, it somehow smooths them out and we get a finite number. And the argument for this is pretty simple. Let's just look at derivatives of A of epsilon. So by this I mean the nth derivative with respect to epsilon of A of epsilon. This is an integral from minus infinity to infinity dt. Derivative with respect to epsilon, which we can write as a derivative with respect to t. And then, because this thing is a Schwartz function and this thing is polynomially bounded at large t, we can integrate by parts. And now we can use our bound on the behavior of f as epsilon goes to 0 to say that the absolute value of this quantity is bounded by some constant over epsilon to the k. Where that constant is given by integrating this function p of t against these derivatives of f of t. Now the key point is that this bound on the derivatives of A of epsilon is independent of how many derivatives we take. And this means that A of epsilon cannot have a singularity as epsilon goes to 0. Because if it had a singularity as epsilon goes to 0, as we took more and more derivatives of that singularity, we would get a stronger and stronger singularity, and we would eventually violate this bound. Another way to say that is that we can decrease the derivative order by integrating. So we could look at a n minus 1 of epsilon, and this is a n minus 1 of some epsilon naught plus the integral from epsilon naught to epsilon of a n of epsilon, the epsilon. And this is bounded by the integral of this, but the integral of this only has a 1 over epsilon to the k minus 1 divergence. And so you can repeat this argument and show that by decreasing the derivative order of A, you decrease the degree of divergence in epsilon. And so if you start this argument with a very large value of n, much bigger than k, then you'll show that A of epsilon is finite. Yes?
So this shows that the A of epsilon is bounded, and does it tell us anything about its single valuedness? What if we have branch cut in the correlation function after analysis?
Good. So the fact that the question is, what if we have a branch cut in the correlation function after analytically continuing? So the key point is that the correlation functions are holomorphic in this region. This region does not depend on the t's. So it means that if we're just varying t, then we never encounter a branch cut. Now the thing that will happen is that as epsilon gets smaller and smaller, we'll get closer and closer to a branch cut, and hopefully I'll draw a picture of that a little later. But we're smearing these things along a direction where we're guaranteed to never encounter a branch cut. Okay. So that's the argument, and I think it's much more instructive to look, well, hopefully equally instructive to look at an example. And the example that we'll look at is a 2-point correlation function in a 1D CFT. And this example, as we'll see later, will lead us to prove the 1D unitarity bound. So we're going to look at an example. 2-point function in a 1D CFT. So this is given by just a power of tau. This is a formula that I wrote earlier. It's fixed by dimensional analysis to be 1 over tau to the 2 delta, where delta is the dimension of O. And so the corresponding Whiteman function is a boundary value of this holomorphic function. So what that means in this case is that OL of t, OL of 0 is the limit as epsilon goes to 0 of what you get when you evaluate this thing at epsilon plus it. So epsilon plus it to the 2 delta. And what this limit really means is something that was made clear in this exercise. This is really a limit in the sense of distributions. So that means that what you should do is integrate this thing against a test function in time and then take epsilon to 0. And that defines a distribution. Okay? And that's really the meaning of this expression. And indeed, whenever anyone uses the I epsilon prescription in quantum field theory, that's the meaning of the I epsilon prescription. Okay? You start with epsilon finite, compute everything that you want to compute, then you take epsilon to 0. Okay, good. So the claim is that this thing is a tempered distribution, and that actually might seem kind of crazy because as epsilon goes to 0, this thing has a terrible, horrible singularity. Let's imagine that delta is 10 to the 10 to the 10 to the 90. Then there's a really, really bad singularity in this thing at t equals 0 as epsilon goes to 0. And it's really surprising that you get a finite result when you integrate it against the test function. Okay?
So you want delta to be that large but not an integer?
No, it's fine if it's an integer. Yeah, okay, sure. Thanks. So it can be an integer or non-integer. It doesn't matter. It's a beautiful tempered distribution. Let's see how this possibly happens. So intuitively, the reason this happens is that so the way I like to think about it intuitively is that when epsilon is non-zero, so what is this thing doing? So as a function of time, this thing is blowing up. And if epsilon is not 0, then it blows up, but then it eventually doesn't. And in fact, if delta is large, what it starts doing is it starts oscillating like this. And then eventually it does that again, right? So that's what you would get if your version of Mathematica had a graphics bug and you tried to plot this function for delta equals 3/2 or something like that. Okay, So it's very oscillatory. So there, maybe it's not so surprising that the integral of this thing is actually finite, even though there's a divergence. And as epsilon goes to 0, these oscillations are in a smaller and smaller regime, but somehow they still define a good distribution. Okay, so you shouldn't think of it as just being infinite at 0. You should think of it as having some structure at 0. And that structure is really important for getting a well-defined distribution. But let's see this more clearly. And the way to really make clear why this is a good tempered distribution is to look at its Fourier transform. So the Fourier transform has a famous property that it takes Schwartz functions to Schwartz functions. So, for example, the first example of a Fourier transform that you ever compute is the Fourier transform of Gaussian, and that's a Gaussian. Okay. So Fourier transform takes Schwartz functions to Schwartz functions, and this allows one to define the Fourier transform of a tempered distribution. This is a really cool idea. The idea is that the Fourier transform of a tempered distribution is just defined by Fourier transforming the argument of the tempered distribution. And this is just a generalization of the usual formula that the integral from minus infinity to infinity dt of f of t times the Fourier transform of some function is equal to the integral where the Fourier transform is swapped. So integral minus infinity to infinity d omega Fourier transform of f of omega g of omega. Okay? So that's a natural property of Fourier transforms on functions, and we can use that to define what it means to Fourier transform a tempered distribution. So let's look at the Fourier transform of this tempered distribution. And when we look at it, we'll see very clearly why it has a nice integral against any Schwartz function. Okay. Okay, so what we would like to do is compute the limit as epsilon goes to 0. Remember, the limit as epsilon goes to 0 is always outside of whatever computation you're doing, because that's the definition of this thing as a distribution. And then we're Fourier transforming it 1 over epsilon plus it to the 2 delta. And so what is the structure of this integral? So we can look in the t-plane, and there's a singularity in the t-plane at I epsilon, and we're integrating along the real axis. And you can see that, so let's suppose that omega is negative. So if omega is negative, then this quantity in the exponent becomes more and more negative as you go into the lower half plane, and therefore the integral is exponentially damped in the lower half plane, and it's holomorphic in that region. Okay, so if omega is negative, you can take the integration contour and deform it to the lower half plane and just get 0. And so that means that we only get a non-zero answer if omega is positive. So there's a theta function of omega. This theta function of omega is really just coming from the fact that the spectrum of the Hamiltonian H is bounded from below. So we're basically just picking out the energies of the system when we're Fourier transforming. And because there are no negative energies, the support of this Fourier transform is only for positive omega. Okay? So there's a theta function. And then, so now let's consider positive omega. In that case, this thing dies in the upper half plane, so we can deform the contour into the upper half plane. And now it encircles a branch point singularity, and we get something non-trivial. And I'll just write the answer, and I'll leave it as an exercise to compute the integral. It's kind of a fun integral. So 2 pi over gamma of 2 delta omega to the 2 delta minus 1. And most of this integral is just fixed by symmetry. So you know from dimensional analysis that it has to be proportional to omega to the 2 delta minus 1. You know from positivity of energy it has to be proportional to a theta function. Okay? Good. So now this thing is obviously a tempered distribution when delta is 10 to the 10 to the 10 to the 90 plus pi, right? It's just, it's what does it look like in omega space? Well, it's 0 for a while, and then it grows with some power. But if you multiply this thing times the Schwartz functions die faster than any power, and therefore you get something whose integral is perfectly well defined. Okay? So the idea is that to check whether it's a tempered distribution, we can look at it in Fourier space, and then it's totally clear. And here I'm using the fact that if I tried to integrate this thing against the Schwartz function, I can instead Fourier transform this thing and Fourier transform the Schwartz function. When I Fourier transform the Schwartz function, it's the result is a Schwartz function. So I end up with an integral of a Schwartz function against this. So let me say it again. So the idea is that we have our 2-point function. Integral of a 2-point function against f of t is the same as the integral of the Fourier transform of the 2-point function against the Fourier transform of f. And what we just saw is that this thing is a tempered distribution. This thing is a Schwartz function, so the result is finite. Yeah, thanks, dt. And actually, this example is kind of cute. So you can say, so clearly this thing is a Schwartz function. Sorry. So clearly this thing is tempered for delta bigger than 0, right? If delta is bigger than 0, then this thing has an integrable singularity at omega equals 0, or no singularity at omega equals 0 if delta is sufficiently large. So it can easily be integrated against a Schwartz function. But we could ask, what if delta is less than 0? And in that case, it looks like this thing fails to be tempered. But actually, that's a problem with the expression and not with the... It's a problem with the calculation that I did and not the actual thing. So the idea is that if delta is less than 0, you should look at it in position space. So in position space, if delta is less than 0, then, again, you clearly get a tempered distribution, right? Because it doesn't have a singularity at t equals... Well, it's not infinite at t equals 0. Okay? So the calculation that I did here was only valid for delta bigger than 0. Bigger than, yeah. If delta is not bigger than 0, then the object you actually get is something that looks like a power law on omega, but it has some structure at 0. That structure is responsible for it having a finite integral against the Schwartz function. And to reveal the nature of that structure, you should go back to position space where it's very clear. Okay, so now let me make some comments. I'm going to try to address your question about smearing and what is the physical meaning and all of that stuff. So this smearing is kind of funny because it introduces these functions, these test functions. And in particular, if you know something about Euclidean CFT, it might make you very uneasy. And it definitely made me uneasy for a long time. And the reason is that in Euclidean signature, smearing does some bad things or some scary things. So one thing that it does is it necessarily involves changing operator orderings. So remember that only time-ordered correlators make sense in Euclidean signature. So if you want to start smearing the times in such a way that they get moved relative to each other, then you're necessarily going to end up taking linear combinations of different orderings of operators. And depending on how well you understand the Euclidean correlator, that might seem like a bad idea. Another thing that it does is it moves you. It can move. A related thing is that the smearing can move outside of the regime of OPE convergence. Okay, so if you have, let's say you have an endpoint function and you have two operators in the middle and you're studying this endpoint function, and the best thing you know about the endpoint function is how to take the OPE between these two operators. But then suppose you want to start smearing them and your smearing function has some overlap with the region where this operator moves outside here. Then the OPE between these two guys becomes invalid. So this taking linear combinations of different orderings of operators, it also bites you in radial quantization. It means that you have to take linear combinations of different OPE regions. And the other problem is that Euclidean singularities are scary. By which I mean they're not integrable in general. Okay, they're of the form 1 over tau, 1 over absolute value of tau to the 2 delta. And there's no structure at tau equals 0 that's going to save you when you try to integrate this thing against a test function. The only thing you can do is integrate this thing against a function that decays sufficiently quickly as tau goes to 0. And how quickly the function has to decay depends on which correlator you look at. Right? If you're looking at correlators of operators of dimension 10 to the 10 to the 10 to the 90 plus pi, you need even nicer test functions. So it kind of looks like a thicket, like something you don't really want to mess with. It doesn't seem like a great idea. And a related thing is that one particular type of smearing is Fourier analysis. Okay, so this is why you don't. So you have to be careful if you do Fourier analysis in Euclidean signature with a reflection positive CFT. You have to Fourier transform singularities like this, and to do that, you need to give some prescription for treating the singularities. And the correct prescription might depend on the physical situation. Okay, so it's not something that you can't do. It's just that it seems like it's not always the most natural thing to do. And I should comment that one situation in which it is very natural to smear and do Fourier analysis in Euclidean signature is for de Sitter correlators. So de Sitter correlators are invariant under the Euclidean conformal group, but the structure of singularities for de Sitter correlators is different from singularities for reflection positive CFTs. And none of these objections really apply in that context. And indeed, people do use Fourier analysis for studying cosmological correlators. It's a pretty natural thing to do in that case. So with the remaining time, let me just contrast this with the situation in Lorentzian signature. So in Lorentzian signature, so first of all, you can smear a Whiteman function. So it doesn't involve changing orderings at all. As we'll see later, it doesn't move you, doesn't always move outside of OPE regions. Hopefully I'll have time to explain that a little bit later. And also, Lorentzian singularities are great. even if they are singular, even if they look horribly unbounded, the I epsilon prescription will always save you. It always gives you a tempered distribution. You can integrate it against a Schwartz function and get a finite number. You should think of Lorentzian singularities. You can think of Lorentzian singularities as like singularities that aren't really there. You're always sort of going around them because of the I epsilon prescription. You're never actually hitting them. And so in particular, Fourier analysis can be a good idea in Lorentzian signature. It involves smearing along these Lorentzian time directions, but the Lorentzian time directions are directions along which the correlator is guaranteed to be holomorphic, and nothing bad is going to happen. And whether it's a good idea to do Fourier analysis or not depends on the symmetries of the problem. And we'll do an example in a little bit where indeed it plays beautifully with the symmetries, and Fourier space is a really nice way to look at a correlator.
Just so you know, David, we're about 1 minute over.
1 minute over. Okay. Good.
So, wrap up.
Okay. I guess I will stop there then and continue next time. Thanks.
Questions? Right here?
So, would the computed results generically depend on how you smear the correlation functions, or?
What do you mean by how you smear?
Could you repeat the question?
Yeah.
I mean,
The question is, do the results depend on how you smear?
Yeah.
So what do you mean by how you smear?
So if you use different test function, what different smearing function, would the results be different?
If you use a different smearing function, would the results be different? Yeah, the numbers you would get would be different.
I
Yeah,
see.
that's right.
In that case, is there like a canonical choice or a natural choice?
Not necessarily, no. It depends on the problem.
Uh-huh.
I guess I want to put the emphasis not so much on the smearing functions. You know, these smearing functions are nice, these smearing functions are not, but on the type of objects that Lorentzian correlators are. The objects that they are tempered distributions. Yeah.
Are these results valid both in perturbation theory and
That's a great question. The question was, are the results valid both in perturbation theory and non-perturbatively? I think that the answer is yes. Although the way in which you do perturbation theory for a tempered distribution, you might have to be careful if you're doing perturbation theory near a singularity. I'm not sure what the general statement is, but I think that it should be okay. The idea would be that you can do perturbation theory at finite epsilon. So you give everything non-zero Euclidean times, and do your perturbation theory, and then later take epsilon to 0. And I think when the epsilons are non-zero, well, it depends on the observable whether perturbation theory works. But if you're looking at an observable where perturbation theory works, or if you're resumming perturbation theory appropriately, then it should work well at finite epsilon. And then when you take the epsilons to 0, you should get reasonable results. But I don't know the fully general statement. Yeah.
So in this part where you said delta should be positive, so that the Fourier transform is either regular or has an individual singularity, is this what would become the unitarity bound if we did this with more work in higher dimensions?
Absolutely. So that's what I was going to do next. So the unitarity bound. So the 2-point function is a tempered distribution no matter what value of delta it is. So you can see that in Fourier space when delta is bigger than 0. You see it in position space, I covered it up, when delta is less than 1. Sorry, Greg. No. But the special thing that happens for delta bigger than 0 is that the Fourier transform is positive. And namely, this gamma function here, gamma of 2 delta, is positive. That's the unitarity bound in 1D CFT. And I'll explain why that's the unitarity bound and also derive it in higher dimensions next time. Yeah?
How should I think of, like, say, UV regularization in this picture? Like, is it a relevant question? Like,
how should you think of UV regularization?
yeah.
So you're imagining trying to perform a path integral.
Yeah.
Good. Let's see. I think it depends on how well you can perform your path integral. If you are doing perturbation theory in a small parameter, then I think you can analytically continue in the coordinates and things will work generally like I said. If you're doing a path integral numerically, like you're doing lattice QCD or something like that, then it could be very hard to implement all of this. Because in order to analytically continue, you need to know the Euclidean, well, so as you guys, I guess, have learned, lattice QCD naturally computes Euclidean quantities. To analytically continue to Lorentzian signature, you need to know the Euclidean quantities really, really well, and it can be hard to do it, and I don't think there's a general prescription for how best to do that. It depends on the problem and how well you're able to do the path integral. In the context of CFT, you can do something kind of different, where you can discover the non-perturbative structure of the correlation functions. You know that they have singularities controlled by operator dimensions, and you can do some regulated path integral to try to compute the operator dimensions as well as you can, and then plug those in and analytically continue the correlator. So again, I don't think there's a general answer. It depends on the problem that you're solving.